Go ahead.
Okay, so we already discussed about the title. It's AeroCom is an initiative that is the aim is to take global models that have aerosol representations in them. They are mostly CDMs, and then you name a comparison, it's happening there. It already happened. They are going to do it. They want to do it, but everything has to do with global aerosol modeling of any type. And the COM part stands for comparison with measurements, and that is one of the weak points of AeroCom, that although there are plenty of data available for the AeroCom community, very few people have worked with data actually, because it is very non-standard. There is a non-standard way of how to save measurements and distribute it to people. Everybody that does measurements save them in their own way, and modelers just love this idea. So they go for the modeling component only. So we try to do the challenge here. Instead of having models, we also have measurements. And in general, the aim of this study within AeroCom is to document the global organic aerosol modeling component in global models, quantify whether the results we get are robust, and whether they are robust because for good causes or for the wrong reasons, why models differ, why models are the same, and also, as I said, how to compare results with measurements. And ultimately, we really want to give ideas on how to improve models. Why there are discrepancies, because there are many, and which components we believe are missing so far from virtually all models. So for modelers, the only thing we really want to do when it comes to aerosols in general is that we want to have, at the same time in a model, chemical and physical properties properly resolved, size distribution, optical properties for the direct effect, CCN formation for the indirect effect, and the time evolution of all these. And in order to do that, we need a finite number of tracers. That is a key point, and it is extremely difficult, especially when it goes to size distribution.
I think finite is not a very high bar. I think it needs to be finite and also
small.
Not more than
exactly.
more than a few.
Yeah. Well, more than a few is, you'll see the number later. It's hard to define few.
Right.
So what's happening? What happened in AeroCom so far? We're currently in phase 2, and the phase 1 ended up in a series of very interesting overview papers, and that was about 2006 and 2007. And in one of them, this is every bar here is a model that was participating back then, and then different colors show different mass contributions to the total aerosol mass. And you see a great deal of variability, especially with regard to aerosol water, which is the dark blue. And but then, even by neglecting water, there are several things that are very different within models. And going to the fine fraction of aerosols only, which is this tiny part here, and a little bit of sea salt and dust, although it shows to be some consensus about what's happening, this, I want to argue that this is for the wrong reasons, because most of the models are using very similar emission inventories. So if you have more or less the same emissions, then you will get more or less the same.
Why are the GISS bars not shown?
Because they didn't provide data for that.
Was that Dorothy?
I believe it was Dorothy and Susanna, yes. And so in this component is the most interesting one for both for the aerosol direct effect, because it's the most efficient scatterer of the aerosols, and is also interesting if you are going to do health studies, because it goes into the lungs and affects human health. So going into present, these are the 13 models. We have 4 different versions of the GISS model. 2 are the bulk model, the bulk aerosols with IPCC, well, semi-5 emissions, and the G-fed biomass burning emissions, which has an annual seasonality instead of decadal. Then it is the GISS matrix and the GISS Thomas. Then there are two other GISS models here that they come from Carnegie Mellon. This is the GISS 2 prime. And the number of organic aerosols, I won't care about how they represent any other things other than organics. And the number of organic aerosol tracers they have ranges from 1 to 62, depending on the model. And for the secondary organic aerosol tracers, 1 to 22, and I'll go back to what this exactly is. So this is an old slide. It shows 27 models out of the real number of 31. And with blue, you see the models that they have a bulk aerosol representation. With brown, you see the ones that have some aerosol microphysics. And then there are two green ones that they are not part of the, in reality they are blue models, but they have them in a different color because they are not part of the official AeroCom database. And these are the different resolutions that you see in the various models, and around 2 by 2.5 or maybe 2.8 by 2.8 is the most common numbers, which is where we are. And as for the number of tracers, most models are having really few tracers. And although the 24 appears here in 4 models, and so it's kind of another peak around 20 or 25. Oh, sorry?
How many do we have?
We have for organics 3, 7, 8.
That's
8.
not enough.
It's not that.
Let me count again. 4, 3, 8. Yeah.
Can you
Why it's
explain?
not there?
Must have pinned it with.
Can you explain what?
Industrial.
What?
8 is industrial, biomass burning, 4 for SOA, primary marine, and MSA, 9. Very good. And these are the two GISS models. And for matrix, it has 3. And for Thomas, I think it has 12.
Can you explain what you mean with tracers?
Tracers is any entity in the global model that you assign a concentration to it, and it can be
you inject it
transported
around.
from one box to the other. And things can happen to it like emissions, deposition, transport, aging, conversion from one entity into another. Anything that generally anything that has a concentration and can be transported is a tracer.
Okay.
And so we tried to simulate the year 2006. We allowed the modelers to use the best approach they had for that year. So we didn't impose to use the same emission inventories or the same meteorology or something, but we just said, based on your expertise, just try to simulate 2006 as close as possible. Then we only focus on surface concentrations, and in one before last slide, I will show you a single plot with vertical distribution. Emissions vary a lot, and both as a magnitude, the variability within the year, the interannual variability, they are quite diverse. But that's not necessarily bad, because we don't know which ones are the correct emissions. So having some variability there is a good thing. And then the organic matter to organic carbon ratio, I'll go into that in more detail, is 1.4. What that means in most models. So what this ratio is the ratio of total organic mass over the organic carbon of that mass. And this is this has to do a lot with the sources of aerosols, and also with the aging of these aerosols, because the more you age an organic compound, the more you go into more oxygenated products, that increases the ratio of OM to OC. So this is a very tricky thing, and very unexplored, and I'll show you more things later for that. So, starting with the models, and I'll have another section for measurements later on. This is a rough idea of how we classified organics. There are organics that are coming from terrestrial sources. This can be anthropogenic or natural. And we also have marine primary sources that they come from the ocean. So bubble bursting that forms, that has some organics in the particles that they are being formed. These two sources are called primary organic aerosols. And you need to remember the term primary. They just come from the moment they are being emitted in the atmosphere, they are aerosols. Then we have the secondary organic aerosols. And these are gases that, through photochemistry, they form aerosols. These can be, that come from, and these come from terrestrial biosphere and human activities. It can be DMS that is being emitted from the oceans, and then it forms methylsulfonic acid in the gas phase. So this forms in the same way aerosols, but this is a single compound, while these ones are thousands. And then we have the aerosol processing. So some aerosols can be oxidized in the gas phase and form something else. I'm not just talking about the simple aging that most models are having. So in the GISS model, we have fresh aerosols that are aging and go into aged aerosols, and that's it. I'm not talking about that. This is has a more chemical meaning, and that changes the properties of aerosols as well. And also there is cloud chemistry that can form aerosols from the gases. So instead of going through photochemistry only, you go through aqueous phase chemistry that also involves photochemistry, of course, that forms aerosols. So these three sources, I will be calling them secondary organic aerosols. And just remember these two terms, primary and secondary for now, and we'll go into more details later. I'll show you this again. So this is what the median model of all 31 is showing. It's on a 5x5 grid, and you see that the maxima are around, this is the annual mean, and you see that the maxima are around tropical forests, also here, through anthropogenic activities, also some biomass burning here. And this is in units of organic carbon, and this is in units of organic matter. And I will call it organic aerosol. And the color bars are the same, so this is a little bit more expected. This is the standard deviation of all these 31 models over the mean. And you see that there is a large variation, and the higher it is, the more the variability against the concentrations that the model are calculating. So you see a really high variability over the Southern Ocean, that the models are, some models are having a source there, some others are not having a source, and that means that we need to really constrain what's happening here. These maxima here are also for the same reason. There are some interesting maxima like this one, or like this one, this one here, that they are correlated with biomass burning. There are some maxima here, which are really strange, and or here. But in general, there are some patterns that you expect. And the interesting thing is that if you see these values, this one is higher than that one, although this one has a higher denominator, which means that the standard deviation overall of that is higher than this one. So the organic aerosol as a term is less constrained than the organic carbon as a trend, as a variability, not trend. And that is because on top of whatever uncertainty there is here and variability, then on top of that you have the organic OM to OC ratio that I just told you that adds up on that and increases the signal. So these are again all the models, and you have the month here and the total source per month, primary organic aerosol emissions. This is the same thing but normalized over the mean of the models, and this is the same thing with that one but with some statistics. This is the mean, this is the 25-75%, and this is the 99 to 91%. And these are the absolute numbers annual mean. And you see that the variability I was telling you. These are the primary sources. The modelers were free to choose whatever they wanted, and the numbers go from something like 30 something like 140 teragrams. We have a factor of 4 difference between these two. And even if you take these two dotted lines, which show the 25 and 75% of the data, you see that there is almost a factor of 2 range for whatever the models we're choosing. And in some cases, the models were really using almost the same emissions, but some small differences make a big difference. Example is this one, these 3 lines. The first green is the GISS matrix model. And then the other 2 green lines are the GISS model E, which have the exact same emissions as matrix, with only one difference, that these ones also have a strong marine source that comes into play. And the difference that you see between these 2 big lines is the difference calculated because of the different climate in the 2 models, because of different wind speeds that are being affected by the different emissions of biomass-bearing. And this model also has a very strong marine source. This model here, the gray one, differs from its sister model in that this one is having another terrestrial biomass-bearing source from plant debris. And I can keep talking for that forever, so let's move on. Secondary organic aerosols. Forget about this 0. I'm still, well, it's negative. I'm still trying to get an answer why we have this number here. And you see that most models are around there, and the number is 19 teragrams per year. It's not a surprise that this number is there, and it has historical reasons. When I was doing my PhD, I was participating in a project that we had to constrain the global amount of secondary organic aerosols being formed. And then during that project, we said, okay, the number is on the order of magnitude is 15% of whatever comes from plants as volatile organic compounds will be converted into aerosols. So right at the time that this project was ending, AeroCom was also starting. And they wanted to have a standard secondary organic aerosol source because it was a very new field and nobody knew how to even model it. So they said, okay, we will take the volatile organic compounds emitted by forests, so that we have some constraints on them, multiply that by 15%, and then get whatever number is there, and we will name that as primary organic aerosol, and we will treat it as such. So so this number ended up to be 19, and many models are using it, still today. And there are some models that don't use it, like these 2 GISS models, and they fall about there. This one is this one is not using it, and it falls a bit lower. This one is not using it, and it's something like double. So there are some important differences here, but about half of the models are still using this 19. And if you remember that some models are having just one organic aerosol tracer, the primary is being emitted into a tracer, and then the secondary is being emitted into the same tracer based on this yield. And that is something that we still try to convince the community to get rid of. This is the load. It highly reflects the emissions, and there is a model that has a funny seasonality, but this also has some very different aerosol formation. And but although this has a marine source that might be skewing this one, but we don't have enough data to be really definite about it. And
is that one of the GISS models?
No, this one is impact. Then the SOA load, that is more tricky, because the formation of secondary organic aerosols is that there is an organic aerosol mass in the atmosphere and some semi-volatile vapors. These vapors will partition between the gas and the aerosol phase, and the more aerosol phase you have, the more you will favor the partition towards the organic aerosol phase. And so if you have a lot of organics, no matter where they come from, that will favor higher SOA formation for the same amount of SOA of volatile organic compounds. And also, if you have different precursor sources, you might have more things that are able to condense on whatever, and that will also affect it. So the noise is much higher. So you can go from something like 0.2 teragrams per year and up to 1.7 teragrams per year, and that's because we have less understanding on that. The total organic aerosol load is the sum of the other two, and you see that there is a big variability. I'm not going to stay more here. The total organic aerosol dry deposition, this is interesting that you see the normalized variability is very highly constrained, and the models follow the very similar patterns, but still there are some very big differences between models. In general, the more organics you have in the atmosphere, the more is available to be deposited. And that is why, for example, this green line, which is the matrix model, deposits much less compared to these two lines, which is the bulk model, because the bulk model has more organics. Then there are these three bars that they have extremely low deposition compared to the other models. Remember, there is no comparison with measurements here, so these might be the correct ones. I'm not going to say that these are the wrong ones, but these are different because they all three have the same aerosol microphysics representation. They are using the M7, it is a 7-bin representation, and all three of them calculate very low deposition rates. Sorry, these ones are...
But the deposition rate really isn't connected to how many different types you have. The deposition rate is a function of this, you know, resistance in series.
That is for gases, not for aerosols.
Aerosols.
Aerosols are depositing because of sedimentation, number one,
right,
and because of
leaf
how,
index.
yeah, some surface processes and some, and also the volatility, the hygroscopicity of the aerosols that says how easily they stick to a surface when they move in Brownian motion. And, but it's less complicated
that's
than that.
that's orthogonal to how many different kinds of traces you have.
That's what you would expect. So these two that are having the M7, and these two, no, so this, and that are having the M7, and they are having very low amounts. This one is having, is Thomas, and that one, give me a second. Okay, so this one and that one, these two are having the Thomas microphysics, and they have very low deposition rates. This one and these two are having the M7, and they have very low deposition rates. These two blue line models here, the green model here, and another that does not have number, they have some other aerosol microphysics, but not the same, and they have very high deposition rates compared to the previous ones. So it is something that has to do with the microphysics that calculates some different properties compared to the other models, and they might be right, and everybody else might be wrong.
Does that also depend on the wet deposition or rain out or whatever?
Wet deposition. Again, very similar pattern, the seasonality, the normalized seasonality, and things are again all over the place, mostly driven by the amount present in the atmosphere, and of course meteorology.
Yeah, so these models also generate clouds and rain and everything. Or is
Most models are CTMs, which means that they read in the meteorology.
Okay, so
And then the few GCMs, most of them except one, I think. Yeah, I think this red one is calculating the climate freely, and the remaining of the GCMs are nudged over against some meteorology.
okay. And if the wet deposition is different, so there's less aerosol. So if the wet deposition is very high in one model, there's less aerosol to leave for dry deposition. So
of course.
So there's also the net deposition or so, or is that just?
I don't think I have the net. No. But the thing is that the wet deposition is either way the dominant removal term for aerosols. So if you see the numbers here, they are in the order of 100, and if you go to dry, this is 15.
Right.
So it doesn't. So if you have double wet deposition between two very similar models, then the amount that remains for dry will be smaller, of course, but the order of magnitude is so different that it will make less of a difference for the dry. And also the dry deposition happens only at surface. Wet deposition happens throughout the column,
Right.
which also makes a difference in also in the distribution. Lifetime, the interesting thing here is that I'm sure you've noticed that many of the models are not submitting things, or we don't have data for everything. So for the models that we have data to calculate the aerosol lifetime, and that is primary, they are kind of all over the place, but also the seasonality is all over the place. There is no real trend here. And these are the primary organic aerosol emissions, organic aerosols, which are supposed to be better constrained, at least with regard to sources. And then the secondary organic aerosols, again, all over the place. Seasonality has no resemblance like they were before. So,
Well, there's some that have some and some that don't.
yeah, exactly. But still, the other ones were really falling.
So I mean, there's a nice clustering there between the bottom ones and the top ones,
Yes.
including ours.
Exactly.
So, yeah, so I mean, that seems to be
So these four models.
an easy explanation.
So these four models are having similar approaches for secondary organic aerosol formation. And the similarity goes into how they treat the volatility of aerosols against temperature. And they are more sensitive to that compared to the other models. And what that means is that when the temperatures are high, so closer to the surface, the semi-volatile compounds that partition between the gas and the aerosol phase are happy to stay in the gas phase unless there are a lot of aerosols around. And then they are being transferred in higher layers, and then in the upper layers there are no clouds anymore. You are above clouds, and everything condenses there because temperatures are really low. So you form a small hazy layer above clouds where temperatures are low, and that is why you have much higher lifetimes, because you have no removal processes there anymore. So in reality, what this shows is that these models are having a source of secondary organic aerosols higher up that does not take into account that you don't have any removal anymore. And I'm going to, that's the total. Okay, this model clearly has an error. I'm still trying to get an answer why this is like this. But that's the total of the two previous ones. I'll skip the optical depth, and that's the summary. So what do we have here? Primary organic aerosols in brown, secondary organic aerosols in green, and total, which is the sum of the two, in blue. Forget this for now. And this is the 25, 75%, 50% of the data, mean, median, and then there are some outliers. And you see that for the sources, primary organic aerosols are have higher sources than secondary, and the total sources are right here. And now let's go to the red one, which is the AeroCom experiments, the old AeroCom experiments. And you see that the variability has increased between the two cases. And this is a 7-year difference between the two studies. And the reason is that in the past, the old AeroCom experiments had a number here. That variability was 0. And then by adding this component here, no matter what happened here, the overall variability increased. And that is evident everywhere. This is the dry deposition, this is times a factor, this is the wet deposition, this is the load, which is more or less the same, and this is the lifetime. And you see the big difference here, the secondary organic aerosols, very diverse compared to the primary organic aerosols, as I just showed you. And another interesting thing is the comparison between AeroCom A and B. AeroCom A is an experiment very similar to what we are doing now. Modelers just simulate whatever you want. AeroCom B says, take the same emissions everywhere and then do the simulation. And you see that the red with the orange bars are not so much different with each other, which means that the emissions themselves, although there is the rule garbage in, garbage out, the emissions themselves are not contributing to the uncertainty. They are not the sole players in the uncertainty. The models do have very big differences because of other factors as well. Let's go to measurements now. I'll go back into the organic carbon to organic matter component in a minute. But before, there is an issue with the aerosol size. That is always a tricky business when it comes to measurements. Because most of the measurements that we're having are filtered measurements, which means there is a filter with small pores, and then particles that pass through it, who cares? Whatever stays on the filter, we measure it. So depending on the filter size, the filter pore size, we are measuring different things. So a typical way is PM1 or PM1.3 in that case, which means particles with diameter lower than 1.3 microns. And you see here, this is zonality at the given station. This is in Finocallia, and it is a remote station in the eastern Mediterranean. And you see there is a seasonality, there is a certain interannual variability. And then this is the PM10 minus 1.3, which means that these are the small ones, these are the big ones. And then you again see a large variability. These are some the times that we have intense dust storms from Sahara affecting the whole Mediterranean region. And this is the annual mean relative contribution on organic carbon of the fine and the coarse mode to the total aerosol mass. So this is something tricky. When you have a model with aerosol microphysics, it means you resolve size. And you can say in principle that I will take exactly the size that my model says, but then if you have sources that they are not assigned properly, then your sizes are skewed because of the problem with the sources. So for example, if you have a plant debris source, which is a coarse fraction of aerosols, then the log-normal distribution of that has a tail that goes into the fine, and that makes comparisons like this tricky, especially when you have models that are having very different sources. And for the organic aerosols themselves, this is that's the total aerosols again. So these are different components in aerosols. It is the same style figure like the previous one, but only for an intense campaign period that lasted about a month. And you see that the fine fraction here has a big variability again. The organics is the green one in here. That also changes from day to day. And you can see also here, the green one is the organic, and that goes into the coarse mode. And how do I put this upside down? So this is the fine mode, this is the coarse mode. So the fine mode is here, these are the green and the organics, and the coarse mode is there. And if you see now, this plot is the same thing with that one, fine mode, but this is the organic carbon concentrations, and this is the organic matter concentrations. And well, it's impossible to see by comparing these two, but one thing that you can see is, number one, the organic matter concentrations, which is measured by the AMS instrument, aerosol mass spectrometry, has a much finer temporal resolution. You see how the line goes up and down, although here it has a much coarser temporal resolution. And then you also see that, well, you can't see, but the variability is not exactly the same here, which means that the organic matter to organic carbon ratio, which was used as 2.2 here, is changing with time. And I told you that the model is mostly having 1.4 in that for that ratio, but there are some models that are calculating that ratio themselves. So they say, okay, every tracer has a different OM to OC ratio given different sources or given different emissions or given different processes. And same units, there is no scale bar, but it goes from 1.4 dark blue to 2.8 red. And you can see that 4 different models have completely different distributions. So we are really having a lot of work to do here. And not only that, but these are in a 5x5 grid, these are the measurements that we use to compare against the models. This is organic carbon urban measurements, and the color scale is the concentration. This is organic carbon remote, and this is organic carbon marine. And you see that mostly it's white. We have no data. So that's all we can do. And these are the organic aerosol measurements. They are now starting to become more and more available. The AMS instrument is something extremely valuable in measurements, and we know that we can get very nice information there, but it is also extremely expensive. So, well, not comparing with satellites maybe. And but people are starting to use it. And you see that this is even more scarce. And this is the number of measurements we have per grid point that I showed you. And you see that mostly is continental United States. And everywhere else it's very few data. So it is what it is, that's what we have. And these are some statistics. The slope here, the mean normalized bias, and the correlation model against measurements for organic carbon and organic matter. And what you can easily see here is that, and these are all for urban stations, you can easily see that all models, forget this one, this has a mistake, and I'm waiting for an update on that. So you see that the urban measurements are always underestimated based on the bias. Correlation is something like 0.4 maybe. And but the interesting thing is that for organic aerosol measurements, that I told you that the models are more diverse when compared with the intra-model variability, the bias is lower and the correlation is higher, which means that the models calculate better organic aerosols. That might lead us to conclude that the emissions that we're getting that have a given assumption for organic carbon matter to organic carbon ratio is something that we need to identify, because that is really an unexpected result. And then for the remote stations, you see that the models perform much better because the correlation is much closer to zero compared. The mean normalized bias is much closer to zero. The correlation is not much better though. But then the organic aerosol measurements by AMS now starts to have a positive bias. So there is something that we don't understand here, and we need to go deeper into what the models calculate and how they calculate organic aerosols in order to be able to do that, to say more things. I showed you that before. I just want you to remember that the primary organic aerosols come from both terrestrial and marine sources, and the secondary organic aerosols come from photochemistry in the gas phase, photochemistry in the gas phase from marine sources, and also from aqueous phase chemistry. And if we take a station here, that's an urban station in Colorado. This is the month, this is the concentrations, and the gray bars is the number of data we have per month. And you see that in an urban station, as expected, all models fail to capture the seasonality. This model that performs great is the one with the wrong numbers. And so you can see here that I've colored some models here with different, with the colors I just showed you before, right here, okay? These have 5 different colors, the arrows, and they are right there. So you see that the models kind of agree that in the summer, the secondary organic aerosols, the green one, is increasing a bit, they kind of agree that well, that's not a very good example. I'll show you in the next one. This is in Colorado, a remote station. And you see that the models capture the seasonality much better, and most of the variability is coming from the change in secondary organic aerosols. So we have plenty of things here. I didn't want to bore you with that. I decided to show you mostly model results, but I have about 1,000 plots like this. Feel free to ask me if you are interested in some part of the world that we have data. This is a station in China.
Oh my gosh.
And you see that the annual mean concentration is 15 micrograms per cubic meter. That's a lot. And that's a remote station. And you see that all models except the wrong one are failing to capture the magnitude. And this is again the station in the in the Eastern Mediterranean. And you see something interesting, that in the top two, I show you the organic carbon measurements. At that station is the only one that we had both filter and AMS data, which means that we had at the same time organic carbon measurements and organic aerosol measurements. And you see that there is a fairly flat seasonality within the year in the organic carbon data, but in the organic aerosol data, although the data points are much less, it appears that there is an increase during summer, when photochemistry is also more active. So it appears that the peak that the models are calculating might be due to the enhanced photochemistry. And remember, I told you that the models are capturing better the variability of organic aerosols, these ones, compared to organic carbon, these ones. And that you can see it by seeing that some models are capturing really nicely that thing, and here no model is really very good to play. And that's my last slide before conclusions. I told you I will show you only one slide for vertical distribution. That's a zonal mean of total organic aerosols, south, north, up to 50 hectopascals here. And as expected, you see that there are plenty of things happening in the tropics, because you have a lot of forests there that contribute to secondary organic aerosols. You have a lot of biomass burning. This is the anthropogenic influence in the total organics, and this is the standard deviation over mean. So models agree, but they are not necessarily correct. They just agree more in the tropical and northern mid latitudes. They strongly disagree in the Southern Ocean region. They strongly disagree in the mid-troposphere in both poles. And then they also disagree a lot higher up. So, and that you can see it here. That is the global mean, annual mean vertical profile in log scale. And you see the difference between models. So, but that's a different paper. Conclusions. The diversity has increased, but the reason is that we have now more processes to simulate and less understanding on how to do that. So we have to work towards that direction. And the missing organic aerosol source can be either anthropogenic or biogenic, or both, of course. The organic aerosol to organic carbon ratio is something very important that is strongly affected by chemistry, by photochemistry, and then if you have more aged aerosols, you can have more, you can have very different effect on climate properties like optical properties, CCN activity, etc. I don't think I have to convince you that the data we have is really scarce and we need many more, but that's not for a modeler to decide. Organic aerosol to organic carbon is the next thing I'm going to work on, and the station-to-station comparison and the vertical distribution has a lot of things to offer. That is for further back, down the way. And I'm done. Yes.
What do the measurements and models say about secondary aerosols of oceans, so from marine origin?
That is tricky. because the marine measurements we have, except one station, are data from ship campaigns, which means one day they're here, the other day they are there, and then they're gone. So it's very difficult to really conclude on that. There is only one station that has some very nice data in the southern Indian Ocean, and it's an island called Amsterdam. It's a funny name, I know. And there they have about 5 years of data, and the models are in general failing to capture the seasonality because the primary marine source is extremely uncertain, virtually unknown. And then the secondary marine source, MSA is fairly straightforward to calculate because it's a simple compound. For the remaining things, it is rather minor. So there are some terpenes and isoprene emitted by the oceans, but they are not really big amounts. So for the marine areas, we need to constrain the primary source, and the community is working towards it, but we are far from it yet.
So what is it we don't understand? Is it we don't understand chemistry, or are there some rates that we can basically tune and
there are two problems primarily. One is that chemistry is extremely complex, both due to the large number of precursor compounds and also the large number of carbons per compound that gives you a very big tree of possible branches throughout the chemical oxidation. The second problem is that even if you are able to have a lumped mechanism for that, you need different tracers for different volatilities that will determine the amount of compounds that will go from the gas phase to the aerosol phase and vice versa. And on top of that, if you are going to do aerosol microphysics, you need to track all these things at the different aerosol populations you have, different size populations you have, and also take into account the kinetics of the equilibrium or not between the gas and the aerosol phase because of size effects. And that takes us far away from the finite number of tracers. And so the main problem we're having is that we're trying to have something extremely simplified for an extremely complex mixture that is far from trivial.
But why is it so simplified? Because otherwise it just blows up? Or
yeah, exactly. You cannot put 1,000 tracers.
You cannot. I mean, also with giant supercomputers.
Exactly.
Okay.
So there are, the people have developed, in Carnegie Mellon, they are doing some very nice work in developing the volatility basis set, which is a function which tracks the evolution of aerosols with time via gas phase oxidation. So you have the organic aerosol, it evaporates, a little, a lot, doesn't matter. That part that evaporated goes into, undergoes chemical oxidation in the gas phase, and then it becomes less volatile because you add oxygens in the molecule, and then it condenses in another volatility bin that evaporates more difficult. On top, so that, let's say you have, so a number that they agree is that if you have 9 volatility bins is enough. Then you have the O to C ratio, which is something very similar to the organic aerosol organic carbon ratio, that shows for every volatility bin, what is the level of aging, of oxidation in that volatility bin. And you might say that you need maybe 10 tracers per bin. So that means 90. And that is for a single aerosol, bulk aerosol population. If you have aerosol microphysics, for example, Thomas has 12 populations. So you need 90 times 12. You can't do it. You just can't do it. So you need to simplify things, and depending on who you're talking to, they simplify different things. So if you are talking to somebody who is doing aerosol microphysics, they will tell you, I'm not going to simplify my microphysics scheme, it is what it is. Simplify your aerosols that you give me for the microphysics. If you're talking to a gas phase person, they will say, no, I don't care about the size distribution of aerosols, I just want the total mass, and I want my gas phase to be correct. It depends. It's a very active area of research, and things will happen in the next 5 years.
When you're doing the comparisons to site measurements, are you just taking the interpolated 5x5 box that this was in?
No.
What are you doing?
I'm taking based on the coordinates of every station, I go into every individual model and select in which box for that model that station is, depending on the resolution.
Okay, so if it was a coastal station, you'd want it to be in a box where there was coast not in the middle of the ocean by accident.
Depending on the local meteorology. So there are coastal stations that you don't really care, right? And there are coastal stations that really matter. For example, there is a very famous station is Mace Head in Ireland, and there are some models that they have the box right above the whole island, but this station always gets in marine air masses from, most of the time, not always, gets marine air masses from the Atlantic, so you're not comparing the same thing.
Right.
But for marine stations like these, it is not, we don't have that many stations like that. And even for Mace Head, we have like 3-4 different months of data, so we cannot really see any seasonality. And a lot of there are some data that they had collected in the past, in Mace Head specifically, that they said, we're going to use an automatic sampler, and every time the wind direction is from the land, it will close. You cannot use that in a model.
Oh, you could. I mean, you just have to process it internally to do that.
Yeah, but in a 2 by 2.5 degrees box, compared to a single meteorological station.
But if they were just going to take, stuff that was coming in off the Atlantic, you would just take a box that was.
Yes, that is a common approach.
So that's what
that is a common approach, yeah. It's the same thing with having altitude problems. Same story.
So you try and pick the right altitude.
Yeah, I tried.
So what is the biggest priority observation-wise? To help constrain the models or improve the models?
Ideally, uniformly spread stations around the globe, as dense as possible. I know that is impossible to have everywhere, but a fairly dense network, especially close to regions that matter, like tropical forests. In Africa, we have 0 measurements. That they are long term. The long term is the trick. There are several campaigns that they were out there for a week. If you don't have the exact same emissions and the exact same meteorology, you're doomed. You don't compare anything. You have to go through climatology. So you need the long-term measurements.
You're saying a satellite-based polarimeter.
That measures column though. It adds an extra level of uncertainty.
Plus LiDAR.
Plus LiDAR, yes, that would be fantastic.
Okay. That's something.
If from that kind of instrument, if you got imaginary refractive index of aerosol from that instrument, would you be able to use that to determine some estimate of organic aerosol or organic carbon?
Imaginary, so this means absorption.
Yeah, if you knew, say a spectral dependence of absorption, would that help?
You need in that case to put an extra level of uncertainty, how much the organics absorb, and whether what we are measuring is absorption because of organics, let's say brown carbon, or it is absorption amplification of black carbon caused by organics around it. There is always an extra level of uncertainty. So if you want to go through that pathway, you need in situ data of organics themselves. Total, speciated, size resolved, or all at once. So the AMS data is excellent because it has very good temporal resolution. It has very good, it has size resolution between 30 nanometers, if I remember correct, up to a micron. And it also gives you information about the chemical composition. It tells you how much is more and how much is less oxygenated. There is also a tracer, not tracer, there is a way to get the biomass burning component of organics. They even try to get the cooking component of organics. So it is an excellent instrument, but if you want to get the really good one, you need $500,000. And that sounds fun. That sounds small in NASA.
From a satellite, it's impossible to actually collect a sample, and whatever information is obtained has to come from reflected light. So it's got to be a radiative property that is used to derive the ratio that you want. So
yeah,
seems like but you were saying you need a size distribution and perhaps a characterization of different aerosol types in order to use imaginary refractive index for.
No, for the imaginary refractive index, you will need to know whether you have absorbing organics or not. Whether the contribution, so you will have a column measurement of of an absorption property, and then you'll have to know whether this is because of organics or something else or both.
Okay.
And you can make assumptions for that based on air masses that you expect, given some other constraints, like even a model. You can run the model and see what the model is suggesting you have there. And you can always use a LiDAR at the same time, so you will at least know the layering. And then from the size information, you can also tell a few things. So even if you have only finite cores, if you see that you have a coarse aerosol population that absorbs, then you can say fairly safely it's dust. And then if you have a fine, then you can say fairly safely that it is dust plus something else, or just something else. So you can make some very good assumptions if you have. I mean, more data is always welcome, no matter what it is. And the trick is how to assign things. And there is a different thing having measurements that will be able to be used to constrain a model, or there will be measurements that will be able to explain why the model is calculating what is calculating. I did the second. So I was not trying to say, these are the organics, so I need to improve the model in that way. I'm only saying that based on what the model is calculating, this is the relative contribution of each component, and probably this is missing. And these measurements will not tell me exactly how to fix the missing component. But I know that based on different models that I see some better and worse performances between them. I know that if there is a better model in a region that has an extra source, I know that I can tell that, this source might be important. Why don't you put it everywhere?